okay? All right, so our test is 4 problems. You know the 4 topics, right? Topic number 1 is free body diagram XY. Problem number 2, free body diagram normal tangential. Problem number 3, energy. Problem number 4, momentum. Okay, we're gonna go through 4 problems today. Hopefully you printed these out. If you didn't, you'll have to follow along quickly. But you know, these are 4 types of problems just to refresh your memory. But even if we don't cover it today, it still might show up on the test. Anything that we've done could show up on the test. In fact, I intentionally try to cover as much material on the test as I can, right? All right, so let's look at this one. Let's look at this one. So for this problem, use free body diagram, particle kinetics. So even though there are a couple of problems that possibly you could use energy on one of these first 2 problems and still get the right answer, I'm looking for free body diagram. All right, so I'm gonna be grading free body diagram, particle kinetics. So the worker pulls with a tension of 400 newtons. Prove that the crate will slip, and then calculate the acceleration of the crate. So this is kind of one of those will it slip type of problems. So the way that I'm going to prove it's going to slip is, first I'm going to assume it will not slip, calculate the force of friction, and then I bet I can compare that to the maximum force of friction. So that's my method of doing these problems. Assume it will not slip, and then calculate the force of friction. So let us assume no slipping. Assume no slipping. Let's draw this free body diagram of the crate, the weight acting straight down, the normal force acting right there, and then we've got this tension that is 15 degrees from the incline. And then we've got the force of friction. The force of friction opposes the impending motion. I think it's going to go up this incline. So my force of friction will be down the incline. Occasionally, you may not know what direction. In this case, maybe that block is so heavy that it's going to go down. My force of friction would come out negative if I draw it the wrong direction. All right, so there's my free body. Those are my forces. I think those are all the forces we have acting on here. Define your axes. It's real important to draw a good free body diagram, draw all the forces, and define your axes. I like to define my axes according to the acceleration. Now, if it's not slipping, acceleration is 0, so I could do whatever axes I want, but I feel like with the normal force and the force of friction and this 15-degree angle, I think it's going to be best to define my axes X and Y, right? Define my axes X and Y. So now, let us sum the forces in the X direction. So T, at this instant, T cosine 15 minus force of friction. Am I going to plug in mu K in? Am I going to plug in mu S in? Or am I going to do neither? I'm going to do neither. This is no slipping. Go back to that one page. There was one page in our notes about force of friction. Go back to that. Make sure you can handle 3 scenarios. If it's slipping, mu K in. If it's on the verge, if it's a maximum, mu S in. But if it's just not slipping at all, then leave it as force of friction. And then this weight, let me break the weight into its 2 components. This is a 20-degree angle. So 59.81 sine 20 would be the X component. Sine 20. And let's write MA. Don't set it equal to 0 too soon, but yes, if it is not slipping, then the acceleration is 0. And actually, I know this T. Sorry, I know this T. 400. 400 cosine 15. All right, so that one equation only has one unknown. So I'm going to go ahead and solve for the force of friction. Force of friction 218.6 newtons. So I need to make sure that's possible. I know the maximum is mu s times n. I haven't found n yet. So let me, how could I find n? Something the force is in the y, right? N minus 59.81 cosine 20. Oh yeah, almost forgot. The tension is also a component of that 400 sine 15 is going up in the positive y. All right, so that equals ma, but is there any acceleration in the y direction? Even when this is slipping, there's still no acceleration in the y direction. One unknown, solve for that, 357.4. So the maximum mu s n 57.4 at this instant would be 178. Maximum 178, so not possible, it will slip. All right, that's how I do these problems. And I think that process works every time. Some of you might be thinking of another way to prove, and I would accept this. So if you like to think of multiple ways to do the same problem, then listen. If you just like the process, then you can stop listening for a minute. How could I prove that this will slip? Well, I could find what force will it barely start slipping, right? What force will it just be on the verge of slipping? So in that scenario, I would set force of friction. All right, so don't listen if this is going to confuse you. That scenario, I would set this to mu sn, and I would just leave t as t, and so I would just solve for t, and I would get, hey, I need a t of 300 something newtons to get it to start moving, and so that would prove that, okay, I'm at 400, so it is moving. So sometimes there are multiple ways to start this type of problem. I like to do mine, and especially mine is helpful because the next step, once it's moving, I don't have to redo everything. All right, I do have to kind of, redo a few of these. Don't have to redo everything. All right, now that I know it is slipping, let me sum my forces in the x direction. Let me sum my forces in the y direction. All right, so summing the forces in the x direction, 400 cosine 15 minus force of friction. So do you see that I'm just taking that x equation that I had previously. I'm rewriting it, though it's going to change a little bit. Now that I know it is slipping, I know the force of friction is mu k 0.4 times n. This weight, 59.81 sine 20 equals, so now I do have some acceleration. Do I know n? Well, sort of. I'm about to rewrite this equation right there. I'm about to sum my forces in y, but it is not going to change, right? Now that it is slipping, this is still the same. It still has no acceleration. So if your equation doesn't change at all, and be careful to make sure it doesn't change. If your equation doesn't change at all, then sometimes, these values, especially for n, these values stay the same. This is still 357.4. I can plug that in right there and solve for AX. 1.51 meters per second squared. 1.51 meters per second squared. So that was just one example, one type of problem, like a will it slip problem. Look back at all those others that we've done. There were some problems where we sum the forces equals mass and acceleration to find the acceleration. And then we took that acceleration and we found the distance that it traveled and the time it took to take. Sometimes the acceleration was constant. Sometimes the acceleration was not constant. Okay. So that's a little bit of a refresher. But, you know, the problems on the test, hopefully, are problems you've never seen before. But this free body diagram, sum of the force equals mass times acceleration. Friction, no friction. I'm just going to try to put friction on some of these problems on the test to see if you can handle, is it kinetic? Do I need to set a US in? Do I need to set it to neither? Okay. All right, so let's look at problem number 2. Problem number 2. Problem number 2, again, free body diagrams. Summing the force equals mass times acceleration. So here we have 2 objects. So I'm going to do the free body diagram for mass 1. I'm going to do free body diagram for mass 2. They might be related. Does this look like one of those like the length problems? L1, L2. Okay, so anyway, at this instant, and we're only looking at this instant, the cable is attached to the cart is tangent. So this is in the all of it's in the tangential direction. At this instant, calculate the maximum speed. So calculate velocity of block 2 such that block 1, okay, such that block 1 barely maintains, you know, contact with the surface. Remember these types of problems. It's going so fast that it's about to kind of fly off, but not yet. So what would that free body diagram look like? If I'm looking at the free body diagram of M1, I've got the tension in that rope. I've got the weight, 0.4, 9.81. All right, so don't draw this. I would draw the normal force of the ground pushing up on that, but do you see that if it's about to lose contact with the road, we're going to set that n equal to 0. We're going to set that n equal to 0. So I think those are the only forces. Pretty easy free body diagram. Let's define our axes. And let's define axes according to accelerations. And so this is in a normal tangential path. So let's define these as normal into the curve. And tangential, I could go either way with this tangential. In general, I like tangential as the direction it's going. And so I'm going to choose tangential right there. Actually, another reason I should choose tangential, if y'all don't mind, let's go ahead and do the L total. You know, do you see that this is, you know, there are two pulleys versus 1 pulley. So it's something along the lines of L total is L1 plus 2 L2s, V1 plus 2 V2s, and A1 plus 2 A2s. These are all positive out. These are all positive out. So to try to stay consistent, I think making that tangent, you know, positive that way, so that this A1 is like the tangential acceleration. So anyway, another reason that I'm going to choose positive that way. Okay, so summing the forces in the normal direction. Okay, let me look at this. Beta is 30 degrees. I see this Z, that's also 30. So that's 30 degrees right here. So summing the forces in the normal direction, 0.4 times 9.81, and that would be the cosine 30 would be in the normal direction. I think that's it. That's the only force in the normal direction. So that equals mass A normal. And what is A normal? Yeah, V squared over R at R 1.75. So this velocity, you know, one equation, one unknown, let's solve. Velocity 3.855. Is that what it asked for? It didn't ask for the velocity of block 1. It asked for the velocity of block 2. So if block 1 is 3.855, block 2, I could put negative. Let me put negative here, because if I plug it into that equation, I would get negative 1.928. What does that negative mean? That negative just means inward. It would be up, which was what it was asking for, the upward speed. So I would take 1.928 is the speed of velocity of block 2. All right, but let's keep going and answer some of the other questions. The other question asks for the acceleration of block 2 and tension in the cord. So let us, I could sum the forces tangential, right? I could sum the forces tangential. So I would say 0.4, 9.81, the sine 30 minus t. All right, y'all listen up. Minus t equals mass times a tangential. And so this is the acceleration of block 1 in this direction. So that would be the same acceleration right there. A1 and A1. I still can't solve, I don't think. I've got that equation has 2 unknowns. I could come back and try to add in that equation, but it also adds another unknown. So I can't solve right away, but I haven't done the free body diagram for block 2, and it has some of the same unknowns. So block 2, its free body diagram, 0.6, 9.81, and it has 2 of these T's, right, 2 of these tensions. And I want this A2 to agree with the acceleration that I'm about to sum the forces equals mass times acceleration. So I'm going to choose positive outward, positive down. I'm going to choose positive down. So now summing the forces in the y direction, positive down 0.6, 9.81 minus 2t equals mass times acceleration A2. So I have this equation right here that has 2 unknowns. This equation right here that has some unknowns. And then this equation up here. I don't know if you can see all those at the same time, but 3 equations, 3 unknowns. Okay, if it's going to take you 15 minutes to solve those 3 equations, 3 unknowns. I hope it does. I hope you can do it real quickly. But if it's going to take you too much time, then you ought to pause right there, make a note, 3 equations, 3 unknowns, and move on, right? Use your time, come back to this. It is worth points solving the math, but the heart of this problem, if you get a good free body diagram and all of your equations are correct, you know, I don't know exactly how much it will be worth, but it's definitely worth more to start problem number 3 and 4 than to finish wrapping up this problem. Okay, but hopefully, hopefully the more of these you do, maybe the better you'll be. But I'd say A1 equals negative 2 A2s, so I'd plug that in right there. Then I'd probably say T is equal to something and plug that in right there, and then solve for T, plug back in, solve for A1, plug back in, solve for A2. Right. All right, this is what I've got. A2, 0.891 meters per second squared. Give me the right units on all your answers. And the tension, 2.68. Tension is 2.68 newtons. Okay. All right, so look back through those problems, especially look back through that skateboarder problem where we drew a free body diagram and it had a theta. And so it wasn't constant acceleration. And so in order to get the velocity, we had to integrate with respect to theta. Remember that problem? Hopefully there was, I don't know, maybe a homework problem kind of like that. I mean, I haven't made the test, but you know, I'm gonna back through all the problems we've done and look at the process. Free body diagram, sum of the forces, free body diagram, and define your axes, normal, tangential. Sum of the forces in normal equals MA normal. Sum of the forces tangential equals MA tangential. Sometimes tangential is into and out of the page, and so we didn't even sum of the forces tangential. We sum the forces, you know, in Z equals MAZ, which might be 0 for some of these. Okay, so that's all for that problem. Let's look at the next one. Look at this next one. All right, so we got a bead with mass of 250 grams. It's released from rest at A and slides down and around the smooth fixed wire. These problems, especially conservation of energy, make sure you understand and are clear where it starts, you know, and where it ends. Because like this one, it kind of draws it at A and B, but it's only one thing. Sometimes it'll kind of draw it in an intermediate point. Sometimes it draws it only at the beginning and it says it goes to B. Make sure you understand. That's definitely something you could ask, you know, to clarify. So does this start right here? You know, yeah, it starts right there at A. I think this one is clear, but some of the other ones maybe aren't as clear. So we're going to use energy. So I would suspect that the first thing you would write on this problem, no matter what problem it is, problem number 3, you know, is energy. Either you want to organize your thoughts and your problems as sigma u equals delta t, or v plus t plus non-conserved work equals v plus t. So this is what I prefer, but you can do whatever you want. I think this is just how I learned it. You know, physics, conservation energy, potential and kinetic, plus any external force distance, like a rope that is being pulled a distance, or maybe something that's drawn on there, maybe friction, but I don't like to do conservation energy with friction. That's that non-conserved work equals v plus t final. So that's what I'm going to do. And I sometimes like to just write the whole equation, even though, you know, I know there's not a spring, but I'm going to write mgh, you know, potential energy due to height, 1/2 kx squared, the potential energy in the spring, plus kinetic energy, 1/2 mv squared, plus fd, but it's only fd if it's a constant force and the distance is in the same direction as the force, equals mgh plus 1/2 kx squared plus 1/2 mv squared final. Right, so this is like the height at A, the x at A, if there was a spring, the v at A here, all this is the final, so at position B. All right, I don't know, just writing that equation makes you feel better when I've got that equation on my sheet of paper, and then I can break it up and think, okay, what's the potential energy? What's the spring energy? What's the kinetic energy? Are there any any external FDs doing any work? Okay, so there's no spring, so I didn't have to write that 1/2 kx squared. It started from rest, did it? I wouldn't expect that. We've done a lot that have started from rest, but I might throw in there just to make it fun, you know, hey, it starts with a velocity of, you know, so many meters per second up at A. Are there any FDs? Is there any external force that does work? We take care of the force due to gravity. We take care of the force in springs, if there was one. There's the only other force here is the normal force of the rod on the collar, but that never does any work, and it's smooth, no friction. In this problem, there's no no non-conserved work. So it's a really short and sweet equation. Potential energy on the left-hand side equals potential plus kinetic on the right-hand side. All right, so MGH, you can set your own ground, you can set your own zero level, but the way we derived it, you have to choose up to be positive, down will be negative. I'm going to choose that to be my ground, right? Because it looks like that's, in general, I kind of like to choose either the beginning point or the ending point to be my ground. That would make the math easier. But this one, I think measuring those distances from that green line might be best. So that's why I'm going to choose that. All right, so the M, and y'all can look here if you really pay attention, really bright here. These three terms that are left all have mass. And I could factor out the mass and cancel that out on both sides. Now, why can I do that? Be careful, because a lot of times you can't do that. You can't do that when you have a spring. If you got that 1/2 kx squared, then you don't have any. There's not mass in there. If you've got this FD, then you probably can't do that. But there are some problems like this one where the mass didn't really even matter as far as we're concerned with the what we're going to solve for the velocity. So, but if there's no problem with having the mass, keeping the mass in there. Okay, so in fact, why not just keep the mass in there? 0.25 grams is the mass. 9.81 is gravity. Remember, don't plug in negative 9.81 for MGH, because we've already taken into account the direction of G. And the height, 0.6, equals 0.25, 9.81. And here the height, only the vertical height, would be that pink line right there. So if this hypotenuse is 0.15, and that's 40 degrees, 0.15 sine 40. All right, 0.15 sine 40. And then 1/2 mv squared. This is only one equation, so I should only have one unknown in my problem, right? There's not like an x equation and a y equation. So, but maybe it's a good sign. I wrote that out. There's only one unknown. I can solve for VB. Right? We're trying to find the velocity at B, and then we're going to find the normal force at B. Velocity at B is 3.14 meters per second. 3.14 meters per second. All right, so now part B, we need to find the normal force N. Normal force N was nowhere in my conservation of energy equation. So, even though this is an energy problem, the heart of this problem, I think, is this energy equation. Part B might be something else, might have to do a free body diagram. So that's what I'm about to do, a free body diagram at B. Now that we know the velocity, let's draw the free body diagram at B to find the normal force between the wire and the bead. All right, so here is this. We've got the weight of the bead, 0.25, 9.81. And then we've got the normal force right there of the rod pushing on the collar. Now, if you got a bead on a wire, a rod that's a collar that's on a rod, it restricts the movement either way. So I actually drew it this way. It might be restricting it the other way. So for a collar, draw it one, or the other. Don't try to do both or anything. If your answer comes out negative, that's fine. I think those are the only forces acting on it. Let's define our axes. according to the acceleration, you notice that this one is in a normal tangential path. So I would define this as my normal direction, that as my tangential. All right, let's think about this 40-degree angle and what angle that is that I just drew. This angle right here would be this angle right here. The bottom right angle is 40. That's going to be a 50-degree angle right there. So free body diagram, defining our axes, and then summing the forces. Let's sum the forces. Normal, 0.25, 9.81 cosine of 50 minus n equals mass times a normal. What is a normal? A normal is v squared over rho, and that v is 3.14 that we have talked about. We have solved for. So we can solve for n. So, I got an n of negative 14.85 newtons. What does that negative mean? It means I chose the wrong direction. Does it kind of make sense? Maybe it makes sense. This bead is going so fast that it kind of wants to go up and out, but that rod is keeping it in. So I drew this the wrong way, but the normal force would be 14.85 newtons right there. It would actually be inward. Okay. Definitely look at springs, right? I like to put a spring on this. Make sure you do the 1/2 kx squared. Remember, 1/2 kx squared, that x is not the length of the spring, it's the amount of stretch or compression of the spring. The potential energy in a spring, 1/2 kx squared. But what if down here at part B, you had to draw your free body diagram? In a free body diagram, you would be drawing the force in a spring, and the force in a spring is not 1/2 kx squared. The force in a spring is kx, k times delta x, k times the amount of stretch or compression. Okay, so please don't mix up, if I give problems like that, that's a very common mistake. Don't mix up the force in a spring with energy in a spring. Also, I could give you a spring problem for one of these other ones, problem 1, problem 2. So know that the force in a spring is k delta x. That might even be on your formula sheet. No, maybe not. So yeah, you got to know that. The energy in the spring, though, is 1/2 kx squared. Okay. Anything else about that type of problem? This might be one of those we've done somewhere. It's energy from A to B, and then maybe a projectile from B to C. But the main heart of it is the energy problem equation. All right, and problem number 4, you already know it's going to be conservation of momentum, but can't you see that this one there's a collision? Either there's a collision, or sometimes it doesn't really seem like it, but like the person that was on the skateboard, the skateboard goes this way, the person goes that way. That's the momentum problem. But in this class, you don't really have to decipher what to use. You already know that problem number 4 is momentum problem. All right, so you got a tennis player that strikes the ball. The ball was going at 10 degrees this way before the collision. Immediately after the collision, it's going at, let's see, so this is 15 meters per second before, 22 meters per second after at 20 degrees. If the 60-gram ball is in contact with the racket for 0.05 seconds. All right, we haven't done much of these. This is a good problem to do. So it tells us the time that the force is in contact with the racket. Determine the magnitude and direction of the average force of the impact of the racket on the ball. Okay. All right, for this problem, more than your conservation of energy problem, for this problem, direction matters. Direction really matters. I'm going to write an X momentum equation, and I'm going to write my Y momentum equation. All right. And the X momentum equation, sometimes if you know the mass of this object and the mass of the other object that are colliding, then we might do the MV of both of them. And then the impulse between the two would be internal, would be equal and opposite. But this one, we only know the mass of that tennis ball. So we're only looking at the tennis ball for this problem. So I'm going to do the MV of the tennis ball plus the FT, right, the impulse, equals the MV of the tennis ball after. So this is initial, and this is, final. And this is X, X, X. I'm only looking in the X direction. Only looking in the X direction. Now, I can only use FT if it's a constant force times time, or in this case, it wants to know the average force. So yeah, I can just take the force times the time. I don't have to integrate, don't have to do integral FDT or anything like that. All right, so here we go. The mass of the ball, 0.06. The initial velocity, only look in the X direction. All right, y'all can go ahead and write it in there. Y'all wrote 15 cosine 10, but what am I leaving out? Yeah, negative 15 cosine 10. Hopefully y'all already had that. Y'all already knew that. Direction matters, pluses and minuses. In fact, maybe I should, I really should define, I should draw my axes. So if my X is to the right, then this is negative 15 cosine 10. All right, plus the force in the X, which I'm looking for, times 0.05 equals 0.06. And its final velocity is to the right, 22 cosine 20. That only has one unknown. I can solve for the force in the X direction, 42.5 newtons. That is the X component of the impulse force, the impulsive force. All right. Now the Y direction, MV plus any FT equals MV, but this is all Y, Y, Y. This is initial, this is final on the right-hand side. 0.06, its initial Y velocity is 15 sine 10, and that one is positive, it is up. Fy, which I'm looking for, times 0.05 equals 0.06, and afterwards it's at 22 sine 20. I can solve for Fy, 5.90 newtons. So the force is 42.5 in the X and 5.9 in the Y. And the problem statement explicitly asks to determine the magnitude and direction. So I would probably accept 42.5 I plus 5.9 J, and I would stop there unless I definitely ask you, if I ask magnitude and direction. Let's find the magnitude of this, right? If it's 42.5 and 5.9, the magnitude would be a squared plus b squared. 5.9 squared, take the square root. 42.9 is the magnitude, and the direction of this theta tangent would be 5.9 over 42.5. I've got a theta 7.9 degrees. So this is, So this is actually not the impulse, that's the force. That's the force. If I was to multiply it times 0.05, then that would be the impulse. That's the force right there. All right, look at those other problems where you had two different masses that you do the momentum of both, and there's an internal impulse. And definitely look at that relative velocity problem. Remember, in these equations, I need to plug in the real velocities. I need to plug in the real velocities. But if I'm given this relative, she thinks she's diving off at this velocity with this angle. That's not the real velocity I need to plug in here. So you got to take a little side note and do, you know, relative VA equals VB plus VA slash V, so that I can plug in the VA, you know, into this equation, not the VA slash V. All right, so I think you have a homework problem, and we did one in class, so I think you should be ready for any of those types of problems. And then we've done some problems, the bullet with the block, and there's no impulse between the bullet and the block, but there was an impulse between the ground and the bullet block. Right? Sometimes the ground can cause an impulse perpendicular to the surface. Okay?